Friends, welcome to the tutorial series on network analysis made simple. This is a module-wise electric circuit analysis paper solution series. In this tutorial, we are going to solve VTU CBCS scheme electric circuit analysis paper of December 2017/January 2018, module 4 of syllabus 15E32. Friends, I prefer to emphasize on basic concepts, strategy and thinking process rather than detailed mathematical steps. I am sure you already are well equipped with the relevant mathematical skills required. Hope this tutorial ignites some of your thoughts. Let's go ahead. Friends, first we shall answer question 1 to obtain the Laplace transform of ramp function tu of t, exponential function e to the power of minus at u of t, and sinusoidal function sin omega t u of t. First consider the ramp function tu of t. We know the ramp function tu of t means it is a unilateral function and is true for t greater than or equal to 0. Also, we know the ramp function is represented as r of t and it is a unit ramp which occurs at t is equal to 0. The given function is tu of t, hence it can be represented as r of t is equal to t. We know by definition L of r of t is equal to integration 0 to infinity t into e to the power of minus st dt. Using the integration by parts, which the rule says u into dv by dt is equal to u into v minus integration v into du by dt into dt. From our equation, let u is equal to t, then du by dt is equal to 1 and dv by dt is equal to e to the power of minus st and v is equal to integration e to the power of minus st dt, and that gives us e to the power of minus st divided by minus s. Friends, integration by parts means L of f of t is equal to first function into integration of the second function minus integral of the second function into differentiation of the first function, which is 1 in our equation. By solving, we get L of r of t is equal to 1 divided by s square. Friends, alternately, we can find the Laplace transform of a ramp function very easily. We know that integration of a step function is equal to ramp function. Therefore, L of t is equal to L of integration of u of t, and that is equal to 1 upon s into L of u of t, which gives us L of t is equal to 1 divided by s square. Very easy, isn't it? Friends, next we shall take up exponential function. The given function is e to the power of minus at u of t, and it can be represented as f of t is equal to e to the power of minus at. Hence, by definition, L of e to the power of minus at is equal to integration 0 to infinity e to the power of minus at into e to the power of minus st dt. By solving, we get L of e to the power of minus at is equal to 1 divided by s plus a. Very simple, isn't it? Next, we shall find the Laplace transform of sin omega t u of t. The given function can be represented as f of t is equal to sin omega t. Friends, by definition we have f of s is equal to integration 0 to infinity e to the power of minus st sin omega t dt. But we know sin omega t is equal to 1 upon 2j into bracket e to the power of j omega t minus e to the power of minus j omega t. By substituting for sin omega t, we get f of s is equal to 1 upon 2j integration 0 to infinity e to the power of minus st into bracket e to the power of j omega t minus e to the power of minus j omega t dt. By using simple algebra and integrating, we get L of sin omega t is equal to omega divided by s square plus omega square. Hope you understood it. Friends, next we shall solve question 2 to find the Laplace transform of the given functions. First consider phi of t is equal to 4s into bracket t minus 2 minus 3t u of t. We know L of v of t is equal to v of s, and that is equal to 4s into L of t minus 2 minus 3 into L of t. By solving, we get v of s is equal to 4 into e to the power of minus 2s minus 3 divided by s square. Next, we shall consider v of t is equal to u of t minus 2 into u of t. We know L of v of t is equal to v of s, and that is equal to L of u of t minus 2. Hence, we get v of s is equal to e to the power of minus 2s divided by s. Very simple, isn't it? Friends, next we shall solve question 3. In this question, we are required to find the circuit current I of t if the switch K is closed at t is equal to 0 in the circuit shown in figure using Laplace transforms. It is given that the capacitor is charged to V naught equal to 1 volt before switching. But what about the initial current IL0 minus in the inductance? We have to find out that. We know at t is equal to 0 minus, K is open, L is short, C is open, and V naught is equal to 1 volt. Incorporating these aspects, the equivalent circuit at t is equal to 0 minus drawn is shown in figure. Observe the network. We find that I0 minus is equal to 0 as K is open. So, IL0 minus is equal to IL0 plus is equal to 0. To find the equation for I of t for t greater than or equal to 0, the circuit for t greater than or equal to 0 drawn is shown in figure. We know the Kirchhoff's voltage equation for the RLC circuit is R into I plus L into di by dt plus 1 upon C into integration I dt is equal to V. But here the voltage applied V is equal to 0. But note that initial voltage across the capacitor V not equal to 1 volt. So we get the equation modified as R into I plus L into di by dt plus 1 upon C into integration I dt is equal to 0. By taking the Laplace transforms, we get R into IFS plus L S IFS minus IL 0 plus 1 upon C into IFS by S minus V0 minus by S is equal to 0. By substituting R is equal to 2 ohm, L is equal to 1 Henry, C is equal to half farad, and Vc0 minus is equal to 1 volt, and rearranging and solving for IFS, we get IFS is equal to 1 divided by S plus 1 whole square plus 1 square. By taking the inverse Laplace transforms, we get I of t is equal to e to the power of minus t sin t. Hope it is clear to you. Friends, next we shall solve question 4. In this question, we are required to state and prove final value theorem. We know that final value theorem helps to find the final value x of infinity or steady state value using Laplace transforms. For that, we should know x of s. Friends, final value theorem states that limit of x of t as t tends to infinity is equal to limit of x of s as s tends to 0. To prove final value theorem, we shall use the operational derivative L of dx by dt is equal to Sx of s minus x of 0. But by definition, L of dx by dt is equal to integration 0 to infinity dx by dt into e to the power of minus st dt. Using the right hand sides of both the equations and applying the limit as s tends to 0, we can write limit of sx of s minus x of 0 as s tends to 0 is equal to integration of dx by dt into e to the power of minus st dt from t is equal to 0 to t is equal to infinity and applying the limit as s tends to 0. Integration of dx by dt into dt is independent of s. Hence, by solving it, we get x of t limits from 0 to infinity, and we can write this as x of infinity minus x of 0 is equal to limit of sx of s minus x of 0 as s tends to 0. By cancelling minus x of 0 on both sides, we get x of infinity is equal to limit of sx of s as s tends to 0. Friends, next we shall solve question 5. In this question, we are required to determine the initial value f of 0 and the final value f of infinity of the given function f of s. We know f of 0 is equal to limit of f of s as s tends to infinity. By substituting for f of s and solving, we get f of 0 is equal to 5 divided by 2. Similarly, we know f of infinity is equal to limit of s f of s as s tends to 0. By rearranging and solving, we get f of infinity is equal to 1. Hope you understood it. Friends, finally, we shall solve question 6. In this question, we are required to find the Laplace transform of the waveform shown in figure. Let me illustrate the strategy. First, obtain the piecewise defined functions of the given waveform. Add all the piecewise defined functions to get f of t of the entire waveform. Finally, find its Laplace transform. So friends, first consider the waveform shown in figure 1. Observe the waveform. We can identify a delayed step of 10 units at t is equal to 2 seconds. Let it be f1 of t, and f1 of t is equal to 10 into u of t minus 2. But at t is equal to 4 seconds, there is a negative step of 5 units, and let it be f2 of t, and f2 of t is equal to minus 5 u of t minus 4. Further, at t is equal to 5 seconds, there is another negative step of 5 units. Let it be f3 of t, and f3 of t is equal to minus 5 into u of t minus 5. By adding all the three piecewise defined functions, we get f of t, and hence f of t is equal to 10 into u of t minus 2 minus 5 into u of t minus 4 minus 5 into u of t minus 5. By taking the Laplace transforms of f of t, we get f of s is equal to 5 divided by s into bracket 2 into e to the power of minus 2s minus e to the power of minus 4s minus e to the power of minus 5s. Friends, finally, consider the waveform shown in figure 2. Observe the waveform. We can identify a positive ramp of 1 divided by 1 equal to 1 unit at t is equal to 0. Let it be f1 of t and f1 of t is equal to r of t. That is simple. But we notice that the given function traces down with a negative slope of minus 1 divided by 1, that is equal to minus 1 unit at t is equal to 1 second. To follow this trace, we need to add a negative ramp of 2 units at t is equal to 1 second. Double the slope, because if we add a negative ramp of 1 unit, the trace follows horizontally as shown. To turn the trace along the given downward direction, we have to add another negative ramp of 1 unit at t is equal to 1 second. So, f2 of t is equal to minus 2 r of t minus 1. If we do so, friends, we see that the trace proceeds downward as shown. To bring the trace along the x-axis, we need to add a positive ramp of 1 unit at t is equal to 2 seconds. Let it be f3 of t, and f3 of t is equal to r of t minus 2. By adding all the three piecewise defined functions, we get f of t, and hence f of t is equal to r of t minus 2r of t minus 1 plus r of t minus 2. By taking the Laplace transforms of f of t, we get f of s is equal to 1 upon s square into bracket 1 minus 2 into e to the power of minus s plus e to the power of minus 2s. Hope you understood it. Friends, for strengthening your basic concepts and developing your thinking process, I suggest you refer my textbooks, Network Analysis Made Simple, Basic Electrical Engineering, Basic Electronics, and Linear Integrated Circuits and Applications, which are available online. Thank you for watching this video.